Let's explore linked lists in the C programming language. A linked list is a linear data structure but with a twist. Instead of storing elements in contiguous memory locations like an array, elements are stored in nodes. Each node contains data and a reference, often called a pointer, to the next node in the sequence. These nodes are connected via pointers, and the memory allocation is dynamic, meaning it can grow or shrink as needed during program execution. Consider a linked list containing the numbers 42, 17, and 9. Each number is stored in a node, and each node points to the next one. The last node points to null, indicating the end of the list. Now let's delve into the structure of a node within a linked list. In the C programming language, we define a node using the struct keyword. Here's an example: struct node. Inside this structure, we typically have two members. First, we have a data element which stores the actual value we want to keep in the list, for instance, an integer. We can define it as int data. Second, we have a pointer to the next node in the list. This pointer is of type struct node pointer, and it's usually named next. To make things more convenient, we can use the typedef keyword to give struct node a shorter alias, like simply node. So each node essentially contains a piece of data and a pointer that points to the next node in the sequence. Let's explore the different types of linked lists. First, we have a singly linked list, in which each node points only to the next node in the sequence. The last node in the list points to null, indicating the end. Traversal is possible only in one direction. Singly linked lists are known for their simple implementation. Next, we have a doubly linked list in which each node has two pointers, one pointing to the next node and another pointing to the previous node. This allows bidirectional traversal, meaning you can move forward or backward through the list. However, doubly linked lists require more memory per node because of the additional pointer. Deletion operations are generally easier in doubly linked lists. Lastly, we have a circular linked list, in which the last node points back to the first node, forming a circle. In circular linked lists, there is no null pointer to indicate the end. Circular linked lists can be either singly or doubly linked, depending on whether the nodes have one or two pointers. These lists are useful for applications like round-robin scheduling, where you need to cycle through a set of elements repeatedly. Let's walk through the process of creating a linked list. Firstly, we define a function called createNode that takes an integer value as input. Inside this function, we allocate memory for a new node using the malloc function. We assign the input value to the data field of the new node. We set the next pointer of the new node to null, indicating that it's currently the last node in the list. Finally, we return a pointer to the newly created node. Now, in the main function, we initialize a head pointer to null, indicating that the list is initially empty. We create the first node by calling the createNode function with a value of 10 and assign the return pointer to the head. To add a second node, we call createNode again with a value of 20, and then we set the next pointer of the first node to point to this new second node. The head pointer points to the first node with the value 10, and its next pointer points to the second node with the value 20, whose next pointer is null. Let's explore some basic operations that can be performed on linked lists. First, inserting a node at the beginning, we create a new node with the given data, set the new node's next pointer to the current head, and then update the head to point to the new node. Next, we have insertion in the middle of a linked list. First, create a new node with the given data, find the position where you want to insert the new node, set the new node's next pointer to the current node's next, and then update the current node's next pointer to point to the new node. Lastly, we have deletion of a node where you find the node before the one you want to delete, update the previous node's next pointer to skip over the node you're deleting, and then free the memory of the deleted node to prevent memory leaks. Let's discuss the advantages and disadvantages of using linked lists. Advantages: dynamic size. Linked lists can grow or shrink during program execution without the need for pre-allocation. Efficient insertions and deletions. Inserting or deleting elements at any position can be done in constant time. That is, order of 1, if the node is known. Memory efficiency. Linked lists allocate memory as needed, so there's no need for contiguous memory blocks. Implementation flexibility. Linked lists can be used to implement stacks, queues, and other data structures easily. Disadvantages. Random access. Linked lists do not allow direct access to elements. You have to traverse from the beginning, which takes order of n time, where n is the number of elements. Extra memory. Linked lists require additional memory to store the pointer references. Traversal complexity. Traversal is slower compared to arrays because there is no locality of reference. Memory management. Linked lists require careful handling to avoid memory leaks and dangling pointers. Finally, some common applications of linked lists include symbol tables, undo functionality, adjacency lists, hash tables, polynomial manipulation, and image viewers. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.